it's week 9, and we are looking at linear regression and classification, right? But before I dive into the topic of the day, I'll just talk a little bit about myself. My name is Lawrence Francis, and I've volunteered like as an instructor and organizer in AI Saturdays Lagos. So currently I'm studying at Carnegie Mellon University. So I'm studying for my master's degree in electrical and computer engineering. Yeah, and like I've like I would say I'm an AI enthusiast because like I'm always working on AI, always working on deep learning.
I think we lost him for a bit. He will be back in a minute.
Hi, I think I got lost.
Yeah, we can hear you now, though.
Okay. So am I able to share my screen again?
Yeah, you
Okay,
kind
yeah.
of. Yeah, made you the co-host.
Okay. Sorry about that. Okay. I think it's back. Okay, yeah. So I think we can just begin. So like I mentioned earlier, this is week 9, and we'll be looking at linear regression and classification. So I learned that I think last week we looked at introduction to machine learning. Yeah, I think it was introduction to machine learning, like where I think Alan discussed linear regression and how to learn from data using a linear regression model. So today we'll be looking at
Lawrence, we can't hear you right now. Don't know if you're speaking.
linear regression, would proceed to work on linear classification as well. Okay, so let's start, right? So please, can I just get if I'm audible, if you guys can hear me.
We can hear you.
Okay. I thought I lost connection again. Okay, that's fine. So we'll start, by considering the equation y equals ax, right? I think last week, Alan, talked about the equation of a line, y equals, I think he used y equals mx plus c, where m is the gradient and c is the intercept. So in this case, we're going to start, not looking at the entire picture, but just considering a subset of what a line is made up of. So we would consider the equation y equals ax, right? And then looking at y equals ax, like having y equals ax in mind, and also looking at this table, right? So I would like to ask what you can say about the relationship between y and x just by observing this table. Like what can you say? Like how is y related to x? Like how can you get y from x? So this table is showing us values for x and also values for y. You can see that when x is equal to 1, y is equal to 2. When x is equal to 2, y is equal to 4. So by just observing this, what can you say? Like how can you obtain y from x? Like if you you can, okay, so I can see someone like on the chart, so you can say y equals 2x. Yeah, by multiplying by 2, that is correct. Yeah, so you have x and you have y, and by just observing this, you see that if you multiply x by 2, you will end up getting y, right? So we can say that y equals 2x, and this is in line with the equation y equals ax, and in this case, a is equal to 2. So we can come up with a scatter plot of this data, of this little data, and we have something like this. And this scatter plot is like it's just showing us the relationship between y and x. Like this just like a perfect like we can draw a perfect line through this. Like it's quite obvious that there's a relationship between y and x. Like a very simple example, and we can go ahead and plot a line that would pass through all the points. Of course, it's going to be a straight line that would pass through all the points. And if you observe this line carefully, it's y equals to x. Yeah. So for any value of x, you get the corresponding value of y by multiplying by 2. So this might sound very simple, but I'm just trying to start from here and then build up on the complexity. So like it might look very simple, but like would get to the complex part shortly. Okay, so given that we know the relationship between y and x, right? So y is equal to 2x. We can use this equation, this y equals to x, to obtain values of y when we know a value of x. So for example, if x is equal to 8, we know that y is equal to 2 times 8, right? So here, when x is equal to 10, what is the value of y? Of course, it's going to be y equals to x, which is y equals 2 times 10, which is 20, right? So there's an exercise here. This is very simple, just like the simple example above of y equals ax. So in this case, you are just meant to observe this table and come up with the relationship between y and x. Well, before I move on, I think I'll just ask, like, if you can tell what the relationship between y and x is from this table. It's very simple. Like, you don't even need to think too much about it. Anyone? Can someone just type something on the chat? Okay, nice. Yeah, yeah, yes. So y equals 3x, right? So this is a very simple example. So this exercise, like for this exercise, you just find a. What is a? Then you create a scatter plot of y against x, just like we did above, and then you plot the line y equals ax. And I think the fourth question is asking you to tell, like, what point does the line at what point does the line pass through the y-axis? So what point 0b does the line pass through? So you can just get that when you draw the line plot. Okay, so let's move a little step further by looking at y equals ax plus b. This equation is similar to what was presented last week in the Introduction to Machine Learning class, where you had the equation of a line, and that equation had the gradient and the y-intercept. So this is similar. So having this equation in mind, y equals ax plus b, what can you say is the relationship between y and x, like from this table here? In the previous example I explained, we just had y equals 2x, and in that case we had assumed that b was 0, so we just had y equals ax without a b. And in this case, I am introducing b, and then I'm just asking you now to come up with a relationship between y and x using y equals ax plus b. What do you think that would be? Like, what do you think the relationship is? I can see y equals 2x plus 1. Someone is saying y equals 2x plus 2. Okay, okay. Wow. Interesting. Okay. Yeah, so everyone could tell that it was y equals 2x plus 2. Yeah. So when we come up with the scatter plot, and then plot the line, right? Like we get y equals 2x plus 2, like which is actually the line that satisfies what is on the table. So it satisfies the relationship between y and x, and in this case a is equal to 2 and b is equal to 2. So there's an exercise here. So for this exercise, you would plot y equals 2x plus b, and in this case b is going to be 3. So you just come up with a line plot, y equals 2x plus 3. Yeah, and after doing that, you tell what point 0b the line passes through. Just a simple exercise, very simple. Okay, so let's look at another example. You have x and y, and in this case now you have something like So when x is 1, y is 4. When x is 2, y is 5. Just something similar to what we've been looking at in the previous examples. So same question, what can you say is the relationship between y and x in this case? Anyone on the chart? So in this case, what can you say is the relationship between y and x using the same equation, y equals ax plus b? What can you say is the relationship? What do you think? Well, I think in this case, it's more difficult to tell, how y is related to x. So to investigate further, we'll come up with a scatter plot, just like we did earlier in the previous examples. And we have something like this, right? So by looking at this scatter plot now, can anyone just, from observation, infer what the relationship between y and x is? Someone said non-linear. Non-linear. Okay, that's interesting. So non-linear separable. Okay, non-linear separable. Okay, so well, y is kind of, I'll say y is related to x in a linear way, right? Because you can come up with a straight line that approximates the relationship between y and x. Just like it was mentioned in the class last week, like where you come up with a line of best fit. So you have a scatter plot, and you want to come up with the best line that fits the scatter plot. And when you do that, you are kind of assuming that there is a linear relationship between the variables that you are modeling. So in this case, we are going to assume a linear relationship, right? Like even though it doesn't seem like it is a perfectly linear relationship, but we would assume a linear relationship between y and x. Okay, so looking at this scatter plot, we can see that some of the points are kind of like we can come up with a line that passes through most of the points. It's very possible. For example, we have this point, this, right? And then a straight line would pass through them. So let's just come up with that line that passes through most of the points. And if we observe, the line that passes through most of the points is y equals 2x plus 2. And we can say that this line, like we can use this line as a line of best fit. So this line fits the points. Like this is the best line that we can come up with, to fit all the points. So like there's no way to come up with a straight line that would perfectly fit all the points, right? But this is the best approximation that we can come up with. Okay, I can see someone just posted y equals half x minus 1. Okay, so that's something that we can plot, like to see to see that relationship also. Okay. So let's now look at another example, right? So in this case, we have same thing, x and y. So like this is a lot of repetition of this, like almost the same example, like just repeating it over and over again. So when we learn, like it's good that we try to learn by repeating examples, and by doing it that way, the concept like would make the concept stick, right? So we have the same example here, not the same, but a similar example of x and y. So same thing, I'll still ask I'll still ask the same question. What do you think is the relationship between y and x, by just observing this? Anyone? Okay. So like if you observe, for the earlier examples, like we are able to just give the answers right away by just observing the table. So by just seeing the table, you can tell what the relationship is. Yeah. Yeah, I can see someone say that the relationship is non-linear. But for the previous examples, like you were able to just tell like how y can be obtained from x. So for the first one, like you're able to just say that y equals 2x. For another one, you were able to say that y equals 2x plus 2, right? But in this case, it's not obvious by just observing it. So let's plot it and see, right? Okay, we've plotted, and mm, can we still, so from this plot, I think we can come up with a line that best, like we can come up with a line that best, explains like how y can be obtained from x, right? So, uh, so like we can do this by just, like we can just, come up with a line, draw a line here, right? And from observation, we can try to come, like we can try to draw a line that best fits, all the data points. So how do you think we can go about this? Okay, I think we would fall back to the equation y equals ax plus b, right? Because that's what gives us a line. And from this equation, like we'll try to find what values of a and b would give us the perfect line. Like would give us the line that best fits these data points. The line called the line of best fit. So we know that we can obtain y from x by using this relationship ax plus b, right? It's quite obvious, and that's the standard. So when you want to get a line, use something of this form, y equals ax plus b. But in this case, we cannot come up with a line that passes through all the data points. It's not possible. And so what we'll do is we'll come up with a line that approximates all the data points. You get? So like for each y, for each y, yeah, we'll try to come up with an ax plus b that is as close as possible to that y. and then would define what we would call an error function. So an error function is something like this, right? So this is an error function. So for each y that we have on the table, we'll try to come up with an ax plus b that is as close as possible to that y. And this error function like just tells how close whatever we come up with is to the y that we have on the table. So this is just for a single data point. We can consider all the data points and subtract whatever ax plus b is from the y, square it, and do that for each data point, right? So for the first data point, we do this. For the second data point, we do this. So for example, like on this scatter plot, for this first data point, like we compute what the error is using the error function, and we do that for all the data points. So that's what this is, right? Okay, so this error function is called the mean squared error. So now we can come up with a function called MSE, which is the mean squared error, such that for all the data points, like we compute an error for a given A and B value. So we can come up with a table, yeah, for a given A and B, we can calculate the error function. So we try probably all possible A and B. Like we can start from a range of A and a range of B, and try to compute the error function, like what the error value would be for that particular A and B. And the goal is to minimize this error. So like we want an A and a B that would give that would result to the least error. So if you observe this table, we have A, B, and for each A, B, we calculate the error function, which is the mean squared error, right? And from this table, we would see that the minimum error is at 11.7. The minimum is at 11.7 because this is the least, like other values are higher than it, right? So it's the minimum. And for this minimum value of the error, we have A as 2 and B as 0, right? And so since we are considering the equation ax plus b, it means that A is 2 and B is 0, and the line that best fits this scatter plot is going to be y equals to x plus 0, which is y equals to x. And when we plot this line, we get something like this. So as you can see, this line is as close as possible to all the data points. So we can call it the line of best fit. So like I would say this is the best line we can get for this like to fit these data points. So if you observe, there was a way we computed A and B. So we found out that A was 2 and B was 0. And how did we come up with that? Like we did these values we came up with these values by searching for all possible combinations of A and B that would result to an error value, and just picked the A and B that resulted to the least error value, as was shown on this table. So we just listed out possible A's and possible B's, computed the error function, and then we picked the values of A and B's that resulted in the least error value. But this technique is not is not an effective technique. Like, I don't expect anyone to list out all the possible values of A, list out all the possible values of B, and then try to compute the error. So like, we should be able to find A and B like automatically, like without having to try out, like keep manually trying out several combinations of A and B. And how do we do this? So there's an algorithm called gradient descent. I'm sure you must have heard of it. So to look at gradient descent, would consider the error function that we calculated above. So for this error function, and like all the possible combinations of A and B that we came up with, would plot the value of the error function against the values of A and B. And we have something like this. So by just observing these two plots, like what do you think is the value of A that gave rise to the minimum error? Anyone? I know it's a simple question, but I think I just have to ask it, right? So yeah, someone said A equals 2, and that's, yeah, of course, it's correct. So if A is equal to 2, we find out that once we compute the error function, like we'll get the minimum value for the error. And in the same vein, for B, when B is 0 and we compute the error function, like would get the minimum value. And in this case, to simplify, to like just for simplification, I fixed B to be 0 for this, and then for this I fixed A to be 2 in this case. Okay, B equals 0. Okay. So yeah, like it's quite obvious. Like when A is 2 would have the least error, and when B is 0 would have the least error. Okay, so what is gradient descent now? Like what is it doing in this case? Like what is it going to help us with? Okay, so with gradient descent, like we can automatically, like by iterating like through different passes of the algorithm, we can come up with the best values for A and B that would give us our line of best fit. So if you consider this plot here, let's use this for like let's use this first one as an example, right? So imagine if A was equal to 2 in this case. So A being minus 2 here, like if A is minus 2, would get an error of, let's say, 500 and something, right? So in this case, what do you think? What do you think would do? Like how do we update A to reduce the error? Like how do we update A? Like if A is equal to minus two, if A is equal to minus two, like how do we update A to reduce the error? So if A is minus two, would have an error of 500 and something. So how do we reduce the error if A is equal to minus two? How do we update A to reduce the error? Okay, someone said we increase A. Okay, yeah, perfect. So if A is equal to minus two, we would have to increase A to reduce the error. That's fine. Then also, if A is equal to, let's say, 6, what do you think would do to A in order to reduce the error? How do we update A in order to reduce the error? Anyone? Perfect. Perfect. So in this case, we would reduce the value of A. So like if A is equal to so if A is equal to 6, would have an error, of say 500, and to reduce that error, would have to, decrease A. And that leads us to the gradient of a function. So what do you think the gradient of a function is? Like when you hear gradient, what comes to your mind? Well, the gradient of a function is like it tells you how that function changes, more of telling you about the rate of change of that function. So like how does this function change with respect to a change in like another variable that function depends on. So for example, the gradient of this error function at this point with respect to A tells me how this error function would change when I change A. So for example, when A is equal to 6, I get an error of say 500, and when I change A by reducing it, the error function reduces, right? Then in this other case, when A is equal to minus 2, I get an error value of say 500, right? And then if I change A by reducing A, sorry, if I change A by increasing A, right, I get a reduced value of the error. So that's what a gradient helps you with. It tells you how will your function change when another variable changes. A variable that the function depends on, like if that variable changes, how would that change affect your function? Okay, so as you had observed from the plot, like would want to work with the gradient, right? And whenever the gradient is negative, like it means that a decrease in the function, yeah, like a decrease in the function would result from an increase in the variable. So like if we have a negative gradient, it means that for this function to decrease, um, the independent variable, that's the A, would have to increase. So if the gradient is negative, for a function to decrease, then the variable has to increase. And on the other hand, if the gradient is positive, so in this case, we have a positive gradient. If it is positive, then for the function to decrease, the dependent variable has to decrease, right? So that was one thing about gradients. And then we can use that in the gradient descent algorithm. So in the gradient descent algorithm, we make updates to the A and B, like using the gradient, right? So such that when the gradient is positive, we decrease A or B, and when the gradient is negative, we increase it with the aim of reducing the error value, right? So this is the update, the gradient descent update. So you calculate the gradient and then you update your value using this gradient. And you don't just do it this way. You would have to introduce something called a learning rate or step size, because imagine you were here at this point, right? And you want to update A in order to reduce the error function, right? And when you are here, you increase A, like in order to reduce the error function, you would have to increase A. And so increasing A means, like, if you increase A too much, you might end up here, and then your error becomes high, right? So what you want to do is you want to take little step, like little updates. You don't want to update A too much. So to update A at this point, you just have to increase it a little. And that's what the learning rate or step size helps you with. So as you can see, the step size or the learning rate multiplies the gradient, and then you update your variables. So A and B would be updated using the gradient multiplied by the step size or the learning rate. Does this make sense, or or I need to go over it again? I think it makes sense. So I think the notebook has been shared on Discord, I believe. But anyways, I can still share it here. All right. Okay, so I've shared the notebook again, but it was previously shared, I think, on the Discord. Like, if you're on Discord, you can there's a link on Discord for the notebook. Okay, so we all know that the error function is given as this, and that so, like, given a function like this, we can compute the gradient of the function with respect to the variables. So the gradient of this function with respect to A is this. You can try to take the derivative by yourself just to confirm. Then the gradient of the function with respect to B is also this. You can also confirm by taking the derivative. Okay, is someone raising hand? Something? Does someone have a question?
Okay, yeah. So
Okay.
of course, I am following up well with the gradient descent and reducing the loss. So, but for the parameters, how do we choose the first parameter and for it to start getting updated, or is the algorithm just going to initialize any value for the parameter and start reducing the loss, or we just initialize without shifting first. I don't know whether you understand.
Okay, if I understand your question, you're asking about gradient descent and how one can use it with an initial values for the parameters. So like, how do you initialize the parameters? Like, how do you come up with initial values for the
Exactly.
parameters? Okay.
Exactly.
Yeah. So one thing about gradient descent is no matter what initial value you start with, is going to converge, right? It's going to keep updating those, like it's going to keep updating the parameter and getting reduced values for the error function, right? Till it gets to the minimum and obtains the optimal parameters. So you can start anywhere, but it's advisable to start with, values that would enable you get to the minimum faster, right? So in this case, like if one starts with 2 as the initial A, of course, like you just need one iteration and you would obtain the optimal value for the error, right? But usually, like we just initialize the parameters randomly for linear regression. So I think there's another case like where you so like if you are working with neural networks or one of those deep learning models, like there's a way for initializing parameters, which is not what we are doing here. Like so for this, like you can start from 0, like just initialize with 0, or you initialize randomly and you let gradient descent take care of it. Okay, so yeah, we need to use a learning rate, like in order not to update too much, right? Okay, so like having understood what a gradient is and how to update parameters using gradient, let's revisit this curve, right? Let's revisit this curve. So looking at that curve, the error curve, when a is equal to -2, what do you think? Like when a is equal to -2, right? And we update a, like how do we update a? So from what we said earlier, right? From what we said earlier, like if a is equal to -2, would have to reduce a in order to reduce the error, right? So let's try to achieve that using gradient descent. So for gradient descent, you start with an initial value of your parameter. In this case, we have a is -2, right? And then we calculate the gradient of a, and with the gradient of a, we update a. So we come up with like a new a. From the gradient, we update a using the gradient. So by doing that, we discovered that so when a is -2, the error is like 500, and then updating it using the gradient, we are getting something like, so a is 230, and then the error is the error increased, right? This is quite a lot. So what do you think is the issue? Like, why did we get something opposite? So the aim of gradient descent is to reduce the error, like update the parameter and reduce the error. So how come we are getting something different? Anyone? How come we are getting something different? Yeah, so I think the issue is with the learning rate, right? So we took too much step, like we went from -2. Of course, we know that we have to increase A, right? Like from what is here. So if you are here, you need to increase A in order to reduce the function. But we increased A too much. So we went from -2 to 230. And that's like somewhere over the limit, right? And in that case, you get you get a very high loss. And that's why we need the learning rate. So in this case, we'd have to introduce the learning rate and set it to a small value of 0.01. Yeah, someone said the learning rate should be too large. And of course, so the learning rate here was actually 1, and 1 seemed like to be a lot in this case. So we'll use a learning rate of 0.01 and use that to update A. And when we do this, like we get something like this. So initially it was -2, and then the function is this. The error function is 486.9, right? And then when we update A, we get a reduced error. And this is what gradient descent does. So you keep doing this. So you start with an initial value of the parameter and you keep, updating it. So let's try that out. So someone is asking, is there a way we can automatically adjust the learning rates? So you can automatically adjust the learning rates before using it, right? So I'm trying to answer this question in terms of linear regression. I don't want to deviate. So for linear regression, just like a simple linear regression like this, you set the learning rate manually, and then you use your you get your gradient and compute the updates. I don't know if you can automatically adjust it. But in the case where you have like a very large data set and you are working with, like, you are performing non-linear modeling, right? And so like in that case, you would have to train longer, right? And you can adjust the learning rate like in such a way that when you start training, right, probably you can start with an initial learning rate, and then you start so like in the process of performing your update of training, like you start reducing the learning rate. I think it's called learning rate decay. Yeah. But like in this case here, in this simple case, you just start with your initial value and use that throughout. So you are asking if there's a mathematical expression. Yeah, if there's a mathematical expression to check and update the learning rate. So what do you mean check? Like, or sorry, like why do you want to update the learning rate? Like, uh, why do you want to do that? Is it to tell whether it is too high or too low? Oh, yeah, since it can be too large or too low. So I don't know if there's an expression like that, but to check if the learning rate is too large or too low, you can just run one update, right? So you run one update, And if that update doesn't result in what you expect, like just like I did here, like in the first case. So I ran a single update, and that single update like didn't give the desired result. So in that case, you know automatically that that this learning rate is too large, right? Yeah, I hope that's an answer. Okay, so moving on. Yeah, so moving on, so we've established, a learning rate, and then we can use that to perform gradient descent, starting with an initial value of A and B. So we just initialize A and B, and then we run the gradient descent algorithm. So initialize B, set your learning rate to 0.01. So in this case, you shouldn't, yeah. So so now if like we know that a learning rate of one is too large, right? So in this case, like we are starting with 0.01, like we are using 0.01 as the learning rate. And then so we compute the gradient. This is a function for the gradient of A, function for the gradient of B, initialize the error to something very large, and we repeatedly, like we just keep on updating A and B using the gradient. So you compute the gradient, use it to update A and B, and you keep doing that till your loss or your error stops decreasing. Okay, sorry. Yeah, so I mentioned that you keep doing that till your error stops reducing. And at that point, you would know that, okay, like I can't do better than this. So you just stop. And whatever values of the parameter you have, you use those values. Okay, thank you. So in this case now, you can see the error plots, and the value of A was obtained to be 2.13, and the value of B was minus 0.27, which is in a way similar to what we had from the random search that we did initially. Okay, so this is gradient descent. This is how it works. This is how you use it to train a linear regression model. So for gradient descent, you come up with an error function, you have your parameters, and the goal is to keep updating your parameters in such a way that your error function keeps decreasing. Okay, so I think we are done with with gradient descent. So I would entertain questions if you have any about gradient descent. If you don't understand it, you can also signify that you didn't understand my explanation, and I can say something. Okay, I think we'll just move on. Seems like everyone understood what gradient descent is. Wow, that was interesting. I think I explained it very well. Okay, so now looking at more than one variable, sorry, this is meant to be more than one variable. Okay, Okay, so for more than one variable, let's look at that. Okay, someone is saying, is gradient descent only applied to linear regression? And the answer is no. So it's not only applied to linear regression. Like you use gradient descent whenever you want to minimize a function. So you have a function that depends on some variables, and then you want to find the values of those variables that would result to a minimum value for that function. You use gradient descent whenever you want to do anything like that. You use gradient descent. And in linear regression, our goal is to obtain the values of the parameters. In this case, A and B. We want to obtain A and B such that the error function is as low as possible. Like what values of A and B would result in the minimum error function, right? That's what we want to do. Yeah, and then we can use gradient descent since that's what gradient descent works for. So there's another algorithm called gradient ascent, right? So it's more like the opposite of gradient descent. So gradient descent is when it's used when you want to minimize, and then gradient ascent is used when you want to maximize. Like you so you want to look for the maximum value of a function, like what values of some parameters would give you the maximum value of a function, right? Yeah, so I hope that answers your question. I think when you start looking into nonlinear modeling, I think probably next week or so, you'll still use gradient descent. And even when you start, looking into more complex models, like you still use gradient descent. So is someone raising hand? Gamaliel or something? Or is it from earlier? Okay, so yeah, let's move on. So for more than one variable, right? So what we've looked at so far is just for one variable. Like we've been looking at one variable. So you have y, and y depends on just x, right? So what if y depends on more than one variable? So what if you have x1, x2, x3, x4, and y depends on all of them, right? So it's still, it's similar to the one variable case. Like you just have to include all the variables. So in the case where you have more than one variable, like so y would be equal to a1 x1 plus a2 x2, like that till the last variable, and then you add b, which is the bias, and to obtain the optimal values of a1, a2 to an that would minimize the error function, use gradient descent. So you can generalize the one variable case. You can generalize it to the case where you have multiple variables. Okay, so let's now look at working with a library. I'm sure we now in a way to some extent we now understand what linear regression is, like how it works, or like how we can compute the parameters using gradient descent. I'm sure we have an idea how that works. Okay, Samuel, you can ask your question.
Yeah, good afternoon.
Yeah, good afternoon.
Yeah. Sorry, I was just trying to run this the libraries. SQL or preprocessing import min max scalar is for what, please? What is it actually doing on this code?
I think I will get there, right?
Okay.
Uh, so min max scalar is just used to scale your features. So you have features that are in different ranges. So one has like a larger range than the other one, and you want them to be in the same range. So once you scale them, they would be in the same range. So one would range between 0 and 1. So the possible values that one would take would be between 0 and 1, and the other one would also take the same values between 0 and 1, like something like that. But I would explain more when I get there um
Okay.
in a bit. Yeah. Okay. So working with a library, like yeah, you've you've understood linear regression, I believe. You've understood how gradient descent works. I also believe. So now let's let's now work with a library that kind of abstracts all the implementation details like from us. So we don't need to bother about updating parameters. We don't need to bother about y equals ax or something. So like we just use the library, and the library would give us a result. So like all these algorithms have already been implemented in these libraries. Like we just need to call them and get them working. Okay, so for linear regression, yeah. So in sklearn, we have a module called linear model that has the linear regression um class, right? Okay, so we'll be working with a data set, uh, a housing data set. You can get the data from Cargo by going to this URL. So you just click on this link. It will take you to the page where you can download the data set. So this is what the data set looks like, right? And the goal here is to perform linear regression using scikit-learn. This is like house price prediction. Like you want to predict the price of a house given some features of the house. Features like the area of the house. So you know the area of the house, and um with the area, like how do you tell what the price of the house would be by just knowing the area? And then we have some other features. So with all these features, how can you predict what the price of a house would be? So let's first consider one of the features or columns as it is here. So let's look at area, right? And coming up with a scatter plot of area, of price against area, we have something like this. So by just looking at this, what do you think is the relationship between price and area? Is it non-linear? Because people keep on, saying it's non-linear. Okay, some said kind of linear. Oh, okay. Uh, yeah, it's linear. It's kind of linear in a way. Anyways, it's linear in a way. Uh, it's positive. We can say it's positive, like it's positive in a way because it's looking as if as the area increases, like we see that the price like also increases with the area in a way, right? But it's not like a perfect positive relationship. You can find this by looking at the correlation and using that to tell. So someone is saying the higher the area, the higher the price. Yeah, you can still say that. Okay, so let's do this same thing for all the features, like the numerical one. Like we'll tackle the categorical ones later on. So for the numerical features, we want to have a scatter plot, right? So we've done for price and area. Uh, So for price and number of bedrooms, we have something like this. For bathrooms, we have this. Okay, this is interesting. Okay, so we can even come up with a correlation matrix, which is something like this. So the correlation matrix just tells us how much, like a particular feature, is correlated with another one. So I don't know if you understand the concept of correlation. So correlation just gives you an idea of the direction, like a particular variable, like how a particular variable responds as a result of changes in another variable. So if one variable increases, does that mean that the other variable would increase? Well, if they are highly correlated, so if they are highly positively correlated, it means that if one increases, the other one would increase would increase also, right? So if you look at the correlation matrix here, you can see that the diagonal entries are all ones, yeah, because well, if you have price and price, of course, it's going to have a high correlation. And mind you, correlation is usually between -1 and 1. So 1 means highly, like a high positive correlation, and -1 is a high negative correlation. And if it is 0, it means like there is no correlation at all. Like it's just so you just have a lot a lot of noise. Like it's not like there is no direction. Okay, so we can also look at a heat map. Like is still the same thing as the correlation matrix, but in this case, like we have some form of visual. And looking at this, which of the pictures do you think is more correlated with the target variable, which is price? Which one is it? Bedrooms? Is it bathrooms? Which one is it? Okay. Yes, it is the area. It is the area. So the area is not a high correlation, but it's it's enough. So it has a correlation of 0.54, which is higher than the other ones. I think the next is bathrooms, which is 0.52. Like if this value approaches 1, like if you have something like 0.9, then it means that it is highly correlated. It's a high positive correlation in that case. So values of 0 means noise, like there is no positive or negative correlation, like it's just randomly scattered. So if you observe the scatter plot for that, you just see the points, randomly scattered. Okay, someone is saying area and bathrooms. That's true because area is 0.54 and bathrooms is 0.52. Okay, so let's build a linear regression model using just one feature. Let's use area, right? Just the area. So this is like performing linear regression with one variable. So we are using just the area, and then the way you use the linear regression in sklearn is you kind of instantiate the linear regression object, and then you call your fit method. You call your fit method, and passing your x value, which is the value that will be used to predict your y. So you're passing your x value and your y value, right? So this would once you do this, you would get I think under the hood, the values for the parameters would be computed. So you would have some form of gradient descent, like under the hood that would come up with what your parameters should be. So after training, we compute the mean squared error for both the train and the test set. Mind you, we had earlier splitted the data set into two. So we have the train set and we have the test set. And we have this. Looking at this, you can say that the error is very large, right? But I think this is the best the algorithm can do for this data set. Like, this is the best it can do. It can't go beyond this. Reason being that you're using just a straight line, and you can only model a linear relationship. So we can plot that. We have price over area, and this is the line that the model came up with for this data. And we're able to plot this line using this. So like we just use y plus ax plus b, right? We found linear regression from sklearn would compute the parameters, and then it will save the coefficient and also the intercept. And when you have access to the coefficient and the intercept, you can use that to compute a straight line. Like, you can use that to find the straight line that best fits the data, which in this case is this red line. So we can go a step further by using two features, right? So we can use the area and the bedroom to train the same linear regression model. So in this case, we would have to use a min-max scalar, or we can use any other scalar, right? But in this case, I chose the min-max scalar. Reason being that if you observe area and bathrooms, you would see that the ranges are different. So the values you have for area are much more larger than the values you have for bathrooms, right? And this is usually a problem for gradient descent. Like, once you pass a data like this to a gradient descent algorithm, the gradient descent algorithm is going to struggle with this. Reason being that the variable for area would have a parameter, and the variable for bathrooms would also have a parameter, right? And when performing your gradient descent updates, you are using a single learning rate. So it's not as if you're using one learning rate to update the parameter associated with area, and another learning rate to update the parameter associated with bathrooms. Like it's just a single learning rate. And imagine taking the same step in, all direction. Of course, when updating the parameter for bathrooms, using the same learning rate as that of area, they're going to take, it's possible to make too much updates for bathrooms because the range isn't that much, right? And then make too little updates for area. So for gradient descent to work well, you need to have them in the same range. And that's why we need to scale, right? So we come up with a scalar. And one of the possible scalars that we have is min-max scalar. And what this does is to scale the values to be between 0 and 1. Okay. So you scale the values to be between 0 and 1. And by doing that, you ensure that they are all in the same range. So you call min-max scalar and you fit it to your data. And what the fit does is to take note of the minimum value and the maximum value in the data. And for you to do the actual scaling, you just call the transform method of the min-max scalar. And by doing that, you transform the features to be in the same range. So here you have area and you have bathrooms, and they will be between 0 and 1. So the reason why you are seeing all zeros here is because I think 1 is like the minimum value for bathrooms, so it's going to be 0. And the maximum value is going to be 1, of course. Okay, so since they are all in the same range, you can call .fit, passing your data, passing your targets, and yeah, you've performed linear regression. So by doing this, you've obtained the best parameters that fit the data, and we can compute the mean squared error for the train set, and we get this. You can see this is also high, right? But it is better than what we had previously. And you can say that, well, it's as a result of having more features and using that for prediction. We can even plot this. So we can have a plot like this. So this just in a way measures the improvement you get, by performing subsequent, fitting. So in the case where you used only one feature, you get a train error and a test error, which is quite high. And by introducing the bathrooms feature, you can see that we get like a much lower error than what we had previously. Okay, so let's also do something else. Let's try to use all the numerical columns, right? So in this case, we are using like area, bedrooms, all the columns that have numerical values. So if you observe, like if you check the data, right? So we have all these columns, and they are all numerical features, right? Because they have numbers, right? So we use them, we add them to our data. Okay, so we use area, bedrooms, bathrooms, the number of stories, and if there's a parking, and then So we extract the numerical features, and then we also perform the feature scaling and normalization. So whenever you are working with more than one variable, so if it is more than one, always ensure that you perform feature scaling and normalization. So they have to be in the same range for gradient descent to do a good job. If they are not in the same range, gradient descent would still work, but it's going to be like it would struggle with it, right? Like I explained earlier. Okay, so we perform the normalization. So using min max, and the values will all be between 0 and 1, and then we train the model and get an error for the train and the test set. And you can see the error. It looks large, right? And so we plot it again. So you can see like we got a better, the model performed better in this case because we had more features. But do you think we can like by adding more features, like would keep getting improved performance? Like do you think that's how to improve, how well your model performs by just adding more features? Is that is that the way forward? Let's see. So let's include the categorical features, right? So in this case, we have these categorical features: the main road, guest room, and the other ones, right? And I don't know if you've been taught this, like who knows how these features would be included, like in the data and be passed into the model for fitting. Like we can just pass them this way, right?
You
Yes.
use a including.
I didn't catch that.
Said you use a one hot encoding.
Perfect. You use one hot encoding. So using one hot encoding is one way of doing this, and there's also another way. There's another way besides one hot encoding. So there's something called label encoding. So instead of using one hot encoding, you can use label encoding. And what label encoding does is just to so if you have two categories, it maps them to numbers. So the first category becomes 0, and the second one becomes 1. So if you have maybe 4, you have 0, 1, 2, 3, 4. First category becomes 0, the next one becomes 1, like that. So we're going to apply label encoding here, and you can get a label encoder from sklearn. And after applying the label encoder, we get this. So you can see they've turned into numbers. And in the case of this main road, where you have just yes, yes, no, yes, right? In this case, you have, so yes became 1 and no became 0. So this is label encoding. And then we add this to the data and fit our model using this. And then you scale, you fit, and then you calculate the error. And we have this. So I think this is lower than what we had previously. So using all the features, like we were able to get a much lower error than what we had. Then we can also try out the one hot encoding, like you mentioned. And I'm sure you are how the one hot encoding works, right? You just consider each of the categories and make them individual features, like such that they would take on like values of 0 or 1, right? Just like you have here. So for main road used to be like a feature on its own, but main road, had two categories, yes or no. So for the one hot encoding, you create another feature for no, create another one for yes, and then where you have no, you indicate by using a 1, and where you have yes, you indicate by using a 1, and then the rest would be 0. Okay, so using the one hot encoding, you train and you get this. As you can see, like you have almost a similar performance as that of label encoding. So this is how you train a linear regression model using sklearn. So you use the linear regression class, use that to instantiate an object, get your data, scale and normalize your data. You fit your model, and then you use your model to make predictions. So now we'll move on to linear classification, right? So, yeah, I think we are done with linear regression. I don't know if anyone has a question about what we discussed in linear regression, like you can ask before we move on to linear classification. Okay, so for linear classification, the goal is just to, you have an input and you want to classify it as being one of a certain number of classes. So in this case, consider this table, like where you have X and Y. So I'm going to start off with a very simple example, just like we did previously. So you have X and Y, and Y can be either negative or positive, right? So you can either have a negative Y or a positive Y, and then X is 0 to 10. So for any given value of X, yeah, you have Y as being either negative or positive. So you have two classes in this case. You have the positive class and the negative class. So someone is asking, how do we know if the model is good for the training for training the data sets? So how you know is first you define the problem. So what task are you trying to perform? If it's linear regression, right? The model to use is the linear regression from sklearn. So you get the linear regression class, right? That was one step. Then another step is to look at your data. So ascertain that your data is um one for linear regression, that your target output is like continuous value, like a continuous value, like something to be predicted, right? So you have that settled, then you can look at your features, right? So your features, like, are they normalized? Like, are they numerical? If they are not numerical, what do? Like, you encode them to be numerical, and with that setup, you can train your model. I don't know if that answers your question, or if your question is deeper than that. Okay. Okay. So what else? Yeah. So we can. Yeah. We have y as either negative or positive. Like it's on the table. We can represent the positive class of y with 1, and then use -1 for the negative class, and then we come up with a table like this, and we can create a scatter plot, and we have something like this. So by just looking at these scatter plots, it's evident that so like intuition will tell you that from these scatter plots, like whenever x is greater than 5, you have a positive y, and if x is less than 5, you have negative, right? Yeah. So like, how do you build a model for this? Well, using what we've learned about linear regression, like you can just use that ideology to create like a line that perfectly fits this scatter plot. So you can just come up with a line, right? And we go back to the line y equals ax plus b, and using gradient descent, we can find the values for a and b that would give us a perfect fit of this scatter plot. And by doing that, we have would have that a is 0.27 and b is minus 1.27. So this is what gradient descent is telling us. So these are the best parameters to use, and when we plot this line, we get this, right? So this line is telling us that like for any value of x, right? For any value of x, like would see that y would either take a positive value or a negative value. For example, if I have like if x is equal to 2, y is going to be minus something, and if x is equal to 6, y is going to be plus something, right? So y is going to be positive for x, greater than 5, I believe, and it's going to be negative when x is less than 5. Okay. So if you look at this, just like I explained, if x is 2, the value of y would be minus 0.73. And for an x that is 10, you see that the value of y would be 1.43. So can you identify the pattern in this? So there's a pattern here that would enable you to classify x as either positive or negative. And that pattern is that whenever ax plus b is less than 0, we get what? A positive class. We get in negative class rather when it is less than 0. And when it is greater than 0, we get a positive class. So as you can see here, whenever for any x, if y is, so this is the 0 mark here. For any x, if y is greater than 0, like would get a positive class, and if y is less than 0, would get something negative, right? So with this intuition, we can come up with something that would call a classification function. So what is this classification function? It's just a function that takes the sign of whatever the output of ax plus b is. So for example, in this case, where x is equal to 2 and ax plus b is minus 0.73, this basically means that the class is -1. That's the negative class, right? And when x is equal to 2 and we have 1.43, we classify this as positive. So when it is negative, we classify it as negative. When it is positive, we classify it as positive. So we have this classification function, which is like the sign of whatever you get from ax plus b. Okay. So yeah, this is just a simple implementation. So this is your h function, which is ax plus b, and your classification function, which is simply the sign of ax plus b. So let's just try out these functions, right? So we have the classification function, and then we evaluate, like we try to classify x equals to 6. So x equals to 6 would be classified as positive, right? Which is evident from here. So x equals to 6 is a positive prediction, right? Then x equals to 4 is negative. So the classification function classifies it as negative. And I think we can try to obtain x equal to 9. So what do you think x equal to 9 would be classified as? What do you think? What do you think x equal to 9 would be classified as? What will it be classified as? It's a simple answer. What is it? Okay, someone said positive. Yeah, that's correct. It's positive. So let's now look at logistic regression and support vector machines. So we've kind of, worked on classification using the ideology from linear regression. So we still use the mean squared error, like we still used the gradient descent from linear regression, like in such a way that the error function was the mean squared error, just like we had in linear regression. And we came up with a line of best fits, right, in that case. And we, did something with a classification function. But that's not like for classification, the goal is not to come up with a line that best fits the data points. That's not what we're interested in. We're interested in a line that best divides the data points. So we're interested in a line that classifies the data points, so it divides them into classes. That's what we want. We don't want a line that fits the data point. So we're not trying to fit the data point. We are trying to let me say divide them, right? We're trying to come up with a line that divides those data points such that you have one class on one side of the line and you have the other class at the other side. And how do we do this? So instead of using the mean squared error function as the loss or error function, we use other error function that have this as an objective. So the mean squared error tries to fit points, and that's not what we are interested in. We are not interested in fitting points. We're interested in classifying, like want a line that divides these points into separate areas. Positives would be on one side of the line and negatives would be on the other at the other side, right? So there's a loss function called the hinge loss, and this loss is in line with the objective of classification in this case. So we know that to come up with a classification, just like I explained earlier, we just look at the sign of of what you get from ax plus b, right? So you compute that and you take the sign, whatever the sign is, So if the sign is positive, then that's the positive class. If it's negative, that's the negative class, right? So what the hinge loss does is to check the sign of h of x. H of x is your ax plus b, right? What you compute, it will check the sign and see if that sign is the same as y. So your correct, your ground truth or your target prediction is y, right? So if y is positive, then h of x has to be positive. Like they should have the same sign. And if that happens, your hinge loss is going to be like won't be that much. But if they are of opposite sign, the hinge loss would be very high. So if you look at the equation for the hinge loss, you can see 1 minus your ax plus b, which is h of x, times y. So if these two are of the same sign, sorry about that. Yeah, so if these two, if h and y are of the same sign, you would get a positive value here, right? And then 1 minus a positive value is going to be low, right? But if they are of different sign, you would have a large negative value, and 1 minus a negative value is going to be 1 plus that, and that would give you like a large loss. So your loss would be high in a way, right? So this loss function has the objective of classification in mind. And then there's also another one called the logistic loss, which also follows the similar idea of checking the sign of wherever the x plus b is and what your target class is. And if they are of the same sign, the loss function like doesn't grow large. But if they are of different sign, like you get a very high loss. So when I say loss, like I'm in a way saying error. You get, so it's just like the error that we looked at for linear regression. Okay, so when you work with these loss functions, yeah. So if you work with the logistic loss, you are doing logistic regression. When you work with logistic loss, you are doing logistic regression. So that is logistic regression. So logistic regression is what we've done so far, but instead of using the mean squared error, like you just use this loss here, and that is logistic regression. And then there's another algorithm called support vector machines. For support vector machines, you use the hinge loss. So for your classification, your loss function is going to be the hinge loss. So just get the hinge loss in here. Use gradient descent to obtain the parameters, and by doing that, you've performed classification using support vector machines, right? Okay, so let's now look at an example. Let's work with the hinge loss. So you can as well do the same thing with the logistic loss, but in this case, let's just consider the hinge loss and move. Yeah, and just show that by using a different loss, other than the mean squared error, like we would attain the classification objective and be able to come up with a line that doesn't fit. Like, so the line we come up with, the aim is not, like, our goal is not to fit the data points with that line. We want to separate the data points with the line. And the hinge loss would help us with that. So if we consider all the data points in our data set, this is what the hinge loss would look like. So this is more like the mean of all the error right? This is the hinge loss, and then we compute the gradient of the hinge loss with respect to A. We'll have something like this. If you perform the derivative, I'm sure you would obtain this. Do we have a question? Okay. I think someone is asking about attendance. Okay. Yeah. And this is the gradient, right? For the bias. Then if you are working with more than one variable, the same equation also applies, only that in that case you would have A1, A2, A3, and all that. So let's now look at the gradient descent with the hinge loss. And in this case, we are looking at two variables, x1 and x2, and we have to classify them as either being negative or positive. Okay, so we have the x1 variable and we have the x2 variable, right? Is someone asking a question? Okay. So we have the x1 variable and the x2 variable, and we have to classify them as either being negative or positive. And now we have, so let's just look at a scatter plot, right? And for the scatter plot, we have something like this. So we have the positives as blue and the negatives as minus, positive as blue and negative as red in this scatter plot. And this is x1 and this is x2. So we'll just jump right in. We'll jump right into gradient descent for this. And this is the gradient descent implementation. So since we have two variables, we will not just have an A, but we'll have A1 and A2, right? Because we have two variables. And also, since we have two variables, we would want to normalize the variables. So we want them to be in the same range because we're working with two variables. We can get away with that if it is just one variable, but if it is more than one, we would have to normalize or scale and normalize, ensure they are in the same range. So we've done that, and then we compute the h function, which is simply a1 times x1 plus a2 times x2 plus b. This is the h function, and this is the hinge loss. Then this computes the gradient with respect to a1, the parameter a1, and then this is the gradient with respect to a2. And then you have this also, and we start gradient descent. So the iterative gradient descent process, we start it here. We start with an initial loss, and then we compute the loss, update the parameters, and we keep doing that till the loss doesn't decrease any further. And yeah, and having done this, so using gradient descent, we're able to obtain A1 as this, A2 as this, and B as this, right? And then we can plot the loss, for each iteration. As you can see, we're able to do about 35,000 iterations of this. And like I said earlier, the goal is not to fit some data points. Like we don't want the line of best fit. We're not interested in that. You only work with line of best fit, like when you are looking at regression, like a line, that fits the data point. No, we don't want that. What we're interested in is a line that separates the data points into two classes. That is what we're interested in. And our h function is a1 times the first feature plus a2 times the second feature plus b. this is our H function, right? So remember what we said earlier about the H function, right? So we said that if the value of the H function is negative, then that is a negative pre-prediction, right? And if the value is positive, then the classification function would give us a positive class, right? That was what we set up earlier, like using the classification function. And the same thing applies here. So we've gotten the H function. And for us to find a boundary, so we call this a decision boundary. The decision boundary is when this H function is equal to 0. So we are going to find a line H of x equals 0, right? That's going to be our decision boundary. And with these parameters, A1, A2, and B, we'll be able to get that line. So if H of x is positive, we have a positive class, right? If it is negative, we have a negative class. Or to put it in a different way, if H of x is greater than 0, we have what? A positive class. If it is greater than 0, we have a positive class, right? And if H of x is less than 0, we have a negative class. So what if H of x is equal to 0? Then we have a boundary. So we have a point that is, in between both classes, right? And with this, we can plot a decision boundary. So H of x equals 0, right? We can obtain the equation of a line from here. So we have x2 equals this, right? And if we plot this, we would get this. So by using the hinge laws, we're able to come up with a decision boundary. We're able to come up with a line that separates the data points. Not a line that fits, not a line that fits the data points. Like, we want something that separates them, right? And that was what we're able to get with the hinge laws. The mean squared error, like if we had used the mean squared error laws, what that would optimize for would be a line that best fits the data points. Like what line is close to all the data points. Like that was what the mean squared error would give us. Like it would try to minimize that error. But in this case, we want a line that separates. I keep repeating this. We want a line that separates the classes. Like we want them separated, and the hinge loss optimizes for that, and the logistic loss also optimizes for that. Okay. So, are there any questions about this? About these losses, point separation, point fitting? Is it well understood?
If anyone has any questions and you prefer to speak, you can just raise your hands.
Okay.
Yeah, I think no one has any at the moment.
I think someone is raising hand. Or something.
Okay, so my question, following the logistic regression, we're mostly talking about that the output would mostly be either a 1 or 0, true or false, or positive or negative. Is that the only outcome? Is that the only class that you can get? because I wanted to know if you can have maybe multiple classes, then we'll now have a decision boundaries with different classes. And that's it. I just want to ask if this you I only encounter two classes. That would be my output for me to give my decision boundary.
Okay. So your question is, if I get, if I got that, the question is for logistic regression. Are you only predicting two classes? Like, is it only 0, 0 and 1, or -1 and 1 that you are predicting? Like, is that your question? Like, are you asking if one can predict more than just two classes?
Yes.
Yeah, of course. So you can use logistic regression to work on a classification problem involving more than two classes. That's possible, right? So I've only touched two classes in this case because so to understand the concept, to understand the concept, like you need to first understand the little detail, yeah, about it. So you need to start from the smallest detail, like so like to understand was like the concept behind an algorithm, like you need to start from the smallest how will I put it, the smallest I think explanation, like, of what's happening. So like you don't start, so like you shouldn't, like if you like to study logistic regression now, like you shouldn't just start with multi-class. Like I think you should start with two classes, understand what's happening, then you move up to more than two classes. Yeah, which is what I'm doing in this case. So I'm starting with two classes and explaining it. So once you can understand, how to classify, how to do a classification that involves just two classes, then you can generalize that knowledge to, more than two classes. So you can, also look at multi-class, like since you understand how it works with just two classes. And even when you move up, like when you go higher to maybe three classes, four classes, it's still the same concept as as it is in the two class case. Yeah, so to answer your question, like of course you can have a problem where you have more than two classes and you can solve it using logistic regression. Okay. So like, do you understand this the decision boundary, like how the classes are separated? Is it Gal? Sorry, I can't pronounce your name.
Okay, it's fine. It's fine. I understand the explanation that you gave.
Oh, okay.
Then I totally understand this.
Okay, yeah. So if you understand this, then you can scale it up to multi-class. So it's still the same idea, right? So yeah, so let's look at the case where you have more than two classes. So in this case, there are two ways, yeah, two approaches. So there's the one versus all. right? So one versus all simply means you consider one class and perform binary classification like on that one class. So you treat that class as a positive class and all other classes as negative, and then you do logistic regression or support vector machines on just two classes. And you perform that for all the classes. So if you have three classes, then you have to come up with three different models. Yeah, if you have four classes, you come up with four different models. So that's the one versus all approach to working with more than two classes. Then there's also the softmax classification, which uses the softmax loss. As you can see, I initially started with the mean squared error loss that we use in linear regression, and that error, the mean squared error, like, is not ideal for classification, so it won't give you, the best result, but it can, approximate what you want, but nobody uses mean squared error for classification. But once you switch mean squared error, once you switch it with maybe the logistic loss, you get logistic regression, right? Then if you instead use the hinge loss, you would get support vector machines, right? Then there's another loss function called the softmax loss. So if you use the softmax loss, you're performing softmax classification, right? And with the softmax loss, you can account for more than two classes with the softmax loss. So if you have three classes, four classes, five classes, and you don't want to go with the one versus all approach where you would have to perform, binary, like that's two class classification for each of the classes, you can just go with softmax classification. But in that case, you would have to introduce the softmax loss in that case. So you can read up on this in the lecture notes. So the reference material for this course is I think the practical data science course, right? So you can read up on this. It's in the lecture notes. So I would have covered softmax classification, but time isn't enough.
Okay, sorry.
Yeah.
Sorry to put you though. From what I understand, okay, I'm seeing that yes, a straight line is helping with the decision boundary to separate maybe the graph from the red dots. But what if maybe everything is kind of mixed per se, not that it's totally mixed, but how having a straight line will I still have to do a straight line decision boundary to still differentiate the classes?
Yeah, so a straight line has a limit. So yeah, so there are problems that a straight line cannot solve. So if something is not, how would I put it? So like, I think next week or one of these, in one of the classes, you would get introduced to nonlinear modeling, something. So like if you have, if there's a nonlinear relationship, like in your data, then like a straight line, like if you use a linear model for that particular problem, then like you just underfit. like a linear model can't solve that, but you can try to probably pre-process your data in such a way that after pre-processing it, yeah, you would establish a linear relationship in your data. So usually, like if your aim is to use a linear classifier or a linear regressor to solve probably a regression or a classification task, you need to ensure that your data, that there's some form of linear relationship in your data. So if you don't have that, then like you won't fit anything you get. So that's why you saw me you saw me I think for the regression task, where is it again? So I plotted the correlation matrix. Yeah, so the correlation matrix just tells you the linear relationship between your features and all that. So if there's no linear relationship, then like a linear model won't work, and you just have to use a non-linear model for that, right? So I think in this case, we are just looking at linear models, like a straight line. Like how can you use a line to classify or to make predictions, right? Okay. So for the linear classification, since we've
Hello?
spent a lot of, okay, yeah, hello. Okay. So for the linear classification, like since we've spent a lot of time, on the regression, we'll just work with like a small data set. From SQLN, we can get the iris data set. So this data set is for classification, and your goal is to classify the iris flower. So you have a flower, and then the features are the length, the width of the sepal, then the petal, the length and the weight. So with these features, like how do you tell what class that the flower belongs to? And the possible classes, we have 3 possible classes. We have the setosa, the very versicolor, and the virginica, right? Okay, so we just go ahead and, like we did earlier, we create a train test plate, and then since we are working with more than one variable, so we have like I think 4 here, 4, right? In this case, you would have to scale and normalize. Very important. So we perform this scale and normalize, and then for logistic regression in sklearn, you can get the logistic regression class. And with this, you can create a model for logistic regression, which you can fit, to your data, and then calculate the accuracy. I forgot to mention, for classification, there's a metric called accuracy that you use to measure like how well your model performs on your data, and it's calculated by counting the number of correctly classified examples and dividing by the total number of examples you have. That's how linear classification works. And sorry, that's how accuracy works, not linear classification. Yeah, so this is how you compute the accuracy, and you use that to judge the performance of your model. For the linear regression, we had used just the error. because we are trying to fit the point, and so we can use the error to judge how well the model is performing. But in this case, we're interested in classification, and so we use accuracy. There are other metrics that can be used, but I think for now, for a start, we just stick with the accuracy of the model. And here we fit the logistic regression, and then we calculate the accuracy score, which is obtained from sklearn metrics. And you do the same thing for the test, and you get this. So what this is saying is we trained with logistic regression, and we got like 92% accuracy. And then the test accuracy is 0.9. And you can do the same for support vector machines. So there's an SVM module where you get linear SVC. You instantiate the model, you fit it to your data, calculate the accuracy, both train and test, and you've done linear classification as easy as it looks. Yeah, and the reference material for this notebook is the lecture notes from the practical data science course. So you can take a look at it if you want to go deeper into some of these concepts and try to understand them. And that's the end. So are there any questions concerning this last part? Okay, if we don't have any question, I think we can call it a day. Thanks everyone for your time. I think we spent more than the allotted time for this. It was meant to be for 2 hours and we went over the limit. Sorry about that. But thanks for your attendance, and I hope you all understand all this. Yeah. So over to you, Fola.
Hi, Lawrence. Thank you so much for today. I think this has been really impactful. I really enjoyed your session. I think the students have as well. If anyone hasn't signed the attendance sheets, please do so. And also you'll be getting your lab 3 assignment results today. So just be on the lookout for that in your emails. Have a great day.